Contactor-controlled panelboard is a common method for controlling power to a specific load or group of loads. The main service fuse disconnect feeds a main lug-only panelboard, which then feeds the contactor. A control system provides a signal to the contactor. When the signal is present, the contactor closes and power is supplied to the second panelboard. When the signal is removed, the contactor opens, and power is removed from the second panelboard. This arrangement is often found in industrial settings. It's used to control power to equipment that isn't constantly needed. It also provides a way to isolate a specific load for maintenance or troubleshooting. This serves as a safety measure, preventing accidental energization of equipment. Firstly, the contactor must be appropriately sized for the load it controls. Secondly, the contactor should be installed in an accessible location for maintenance and troubleshooting. Thirdly, the control system must provide a reliable signal to the contactor. Contactor-controlled panelboards are a safe and effective way to manage power to specific loads or groups of loads. They are relatively simple to install and maintain, offering a high level of control over the electrical system. When selecting a contactor for a panelboard application, several factors must be considered to ensure proper operation and safety. Firstly, voltage rating. The contactor's voltage rating must be equal to or greater than the system voltage. For example, in a 480-volt system, the contactor should have a voltage rating of at least 480 volts. Secondly, current rating. The contactor's current rating must be sufficient to handle the maximum current drawn by the load. This rating is typically given in amps. To determine the appropriate current rating, calculate the full load current of the load and then apply a safety factor. Thirdly, horsepower rating. For commercial loads, the contactor must have a horsepower rating equal to or greater than the motor's horsepower. This rating indicates the contactor's ability to handle the inrush current associated with starting a motor. Fourthly, number of poles. The number of poles on the contactor should match the number of conductors being switched. For example, a three-phase system requires a three-pole contactor. Fifthly, coil voltage. The contactor's coil voltage must match the voltage of the control signal used to energize the contactor. Common coil voltages include 24 volts alternating current, 120 volts alternating current, and 24 volts direct current. Sixthly, auxiliary contacts. Auxiliary contacts provide additional switching functions such as interlocking or status indication. Consider whether auxiliary contacts are needed for the specific application. Seventhly, environmental conditions. The contactor's enclosure should be suitable for the environmental conditions in which it will be installed. Factors to consider include temperature, humidity, and exposure to dust or corrosive substances. Eighthly, standards and certifications. Ensure that the contactor meets relevant standards and certifications, such as Underwriters Laboratories or Canadian Standards Association, to ensure safety and performance. Selecting the right contactor involves careful consideration of these factors to match the contactor's capabilities to the demands of the specific application. Consider a scenario where you have a panelboard feeding a large piece of industrial equipment that needs to be shut down remotely for safety reasons. The equipment operates at 480 volts and draws 100 amps. Firstly, voltage rating. You would select a contactor with a voltage rating of at least 480 volts. Secondly, current rating. Choose a contactor with a current rating higher than 100 amps, for example, 125 amps to provide a safety margin. Thirdly, horsepower rating. If the equipment includes a motor, ensure the contactor's horsepower rating is sufficient for the motor's horsepower. Fourthly, number of poles. For a three-phase 480-volt system, select a three-pole contactor. Fifthly, coil voltage. Determine the control voltage available, such as 120 volts alternating current, and select a contactor with a corresponding coil voltage. Sixthly, auxiliary contacts. If you need to monitor the contactor's status remotely, select a contactor with auxiliary contacts. Seventhly, environmental conditions. Choose a contactor with an enclosure suitable for the industrial environment, such as a National Electrical Manufacturers Association 4 enclosure for protection against dust and water. Eighthly, standards and certifications ensure the contactor is UL listed to meet safety standards. By carefully considering these factors, you can select a contactor that meets the specific requirements of the Panelboard application, ensuring safe and reliable operation of the equipment. Panelboard configurations and wiring depend on the specific application and the loads being served. However, some general principles and common practices guide the design and installation of panelboards. Firstly, main breaker or main lugs only. Panelboards are typically configured with either a main breaker or main lugs only. A main breaker provides overcurrent protection for the entire panelboard, while a main lugs only panelboard requires a separate upstream overcurrent protective device, such as a fuse disconnect or circuit breaker. Secondly, branch circuit breakers. Branch circuit breakers protect individual circuits that feed various loads. The size and number of branch circuit breakers depend on the number and size of the loads being served. Thirdly, neutral and ground buses. Panelboards include neutral and ground buses for terminating neutral and grounding conductors. These buses provide a common point for connecting these conductors, ensuring proper grounding and minimizing the risk of electrical shock. Fourthly, feeder conductors. Feeder conductors supply power to the panelboard from the upstream of a current protective device. The size of the feeder conductors must be sufficient to carry the total load served by the panelboard, in accordance with the National Electrical Code. Fifthly, wiring methods. Wiring methods for panelboards must comply with the NEC and local codes. Common wiring methods include using conduit, cable trays, and wireways to protect and support conductors. Sixthly, bonding. Panelboards must be properly bonded to the building's grounding system to provide a low impedance path for fault current. Bonding is typically achieved by connecting the panelboard enclosure to the grounding electrode system with a bonding jumper. Seventhly, labeling. Panelboards should be clearly labeled to identify the circuits and loads being served. Labeling helps with troubleshooting and maintenance, and it ensures that the correct circuits are de-energized when necessary. Eighthly, clearances. Adequate clearances must be maintained around panelboards to provide access for maintenance and prevent obstructions. The NEC specifies minimum clearance requirements for working space around electrical equipment. Ninthly, overcurrent protection coordination. Overcurrent protection devices within the panelboard should be coordinated to ensure that the smallest overcurrent device closest to the fault opens first, minimizing the extent of the outage. Tenthly, arc flash hazard analysis. An arc flash hazard analysis should be performed to determine the potential arc flash hazard of the panelboard. The analysis helps determine the appropriate personal protective equipment needed to work safely on or near the panelboard. These principles and practices provide a framework for designing and installing panelboards that are safe, reliable, and compliant with applicable codes and standards. Let's consider a scenario where you are installing a 200 amps panelboard in a commercial building. The panelboard will serve lighting, receptacles, and HVAC equipment. Firstly, main breaker or main lugs only. You can choose either a panelboard with a 200 amps main breaker or a main lugs only panelboard connected to a 200 amps upstream breaker. Secondly, branch circuit breakers. Install branch circuit breakers of appropriate sizes for the lighting, receptacle, and HVAC circuits. For example, 15 amps breakers for general lighting and receptacle circuits, and larger breakers for HVAC equipment. Thirdly, neutral and ground buses. Connect the neutral and grounding conductors to the respective neutral and ground buses in the panelboard. Fourthly, feeder conductors. Size the feeder conductors from the upstream breaker to the panelboard to carry at least 200 amps, based on the NEC ampacity tables. Fifthly, wiring methods. Use conduit to protect and route the feeder and branch circuit conductors to the panelboard. Sixthly, bonding. Bond the panelboard enclosure to the building's grounding electrode system with a bonding jumper. Seventhly, labeling. Clearly label each circuit breaker with the description of the load it serves, such as lighting, receptacles, or HVAC. Eighthly, clearances. Ensure that there is adequate working space in front of the panelboard, typically at least 3 feet, to allow for safe maintenance and operation. Ninthly, overcurrent protection coordination, coordinate the branch circuit breakers with the main breaker to ensure selective tripping in the event of a fault. 10thly, arc flash hazard analysis. Conduct an arc flash hazard analysis to determine the potential arc flash hazard and select appropriate personal protective equipment for workers who may need to work on the panel board. By following these steps, you can properly configure and wire the 200 amps panel board to meet the electrical needs of the commercial building while ensuring safety in compliance with codes and standards. Troubleshooting a contactor-controlled panel board involves systematic steps to identify and resolve issues efficiently. Firstly, visual inspection. Begin with a thorough visual inspection of the panel board, contactor, and associated wiring. Look for signs of damage, loose connections, or overheating. Secondly, voltage testing. Use a multimeter to verify that the correct voltage is present at the panel board's input terminals and at the contactor's coil. Check for proper voltage levels and any voltage drops. Thirdly, continuity testing. Perform continuity tests on the control circuit wiring to ensure that there are no open circuits or shorts. Check the continuity of the contactor's coil to verify its integrity. Fourthly, control signal verification. Verify that the control signal is present at the contactor's coil terminals when the control system is activated. Use a multimeter to measure the voltage or current of the control signal. Fifthly, contactor operation. Manually operate the contactor to verify that it opens and closes properly. Check for any mechanical issues or binding. Sixthly, load testing. Use an ammeter to measure the current drawn by the load when the contactor is closed. Compare the measured current to the expected current to identify any load-related issues. Seventhly, component testing. If specific components are suspected of being faulty, test them individually using appropriate testing methods. For example, test the control system's output module or the contactor's auxiliary contact. Eighthly, wiring insulation testing. Use a megometer to test the insulation resistance of the wiring. This test can help identify insulation breakdown, which can cause ground faults or short circuits. Ninthly, thermal scanning. Use a thermal imaging camera to scan the panel board, contactor, and wiring for hotspots, which may indicate loose connections or overloaded circuits. Tenthly, documentation review. Review the panel board wiring diagrams and documentation to ensure that the wiring and components are installed correctly. Refer to the manufacturer's specifications for the contactor and other components. These steps provide a systematic approach to troubleshooting contactor-controlled panel boards, enabling technicians to quickly identify and resolve issues, ensuring safe and reliable operation of the electrical system. Let's consider a scenario where the second panel board fed by the contactor is not receiving power. Firstly, visual inspection. Check the panel board and contactor for any obvious signs of damage, loose connections, or burnt component. Secondly, voltage testing. Use a multimeter to verify that the correct voltage is present at the input terminals of the first panel board and at the input and output terminals of the contactor. If there is voltage at the input but not the output of the contactor may be the problem. Thirdly, continuity testing. Check the continuity of the wiring between the first panel board, the contactor, and the second panel board to ensure there are no open circuits. Fourthly, control signal verification. Verify that the control signal is reaching the contactor's coil when the control system is supposed to activate the contactor. If the control signal is missing, troubleshoot the control system. Fifthly, contactor operation. Try manually operating the contactor to see if it closes and provides power to the second panel board. If it works manually but not with the control signal, the contactor coil or control circuit may be faulty. Sixthly, load testing. Once power is restored, measure the current drawn by the second panel board to ensure it is within the expected range and that the contactor is not overloaded. Seventhly, component testing. If the contactor is suspected of being faulty, test its coil and contacts individually to determine if they are functioning correctly. Eighthly, wiring insulation testing. Use a megometer to check the insulation resistance of the wiring, looking for potential shorts or ground faults. Ninthly, thermal scanning. Use a thermal imaging camera to check for any hotspots on the contactor or wiring, indicating potential overheating or loose connections. Tenthly, documentation review, refer to the wiring diagrams and manufacturer's specifications to ensure that all connections and settings are correct. By systematically following these troubleshooting steps, you can efficiently diagnose and resolve the issue of the second panel board not receiving power, ensuring the safe and reliable operation of the electrical system. The NEC provides specific guidelines for sizing conductors and overcurrent protection for panel boards, ensuring safety and compliance. Firstly, conductor ampacity. The ampacity of the conductors feeding a panel board must be sufficient to carry the calculated load, as determined by NEC Article 220. The load calculation includes both general lighting and receptacle loads, as well as specific loads such as motors and HVAC equipment. Secondly, overcurrent protection. The overcurrent protection device, such as a circuit breaker or fuses, must be sized to protect the conductors from overloads and short circuits. The NEC specifies the maximum allowable overcurrent protection for different conductor sizes in NEC Table 310.15b16. Thirdly, main breaker or main lugs only. If the panel board has a main breaker, the breaker must be sized to protect the panel board's busbars and internal components. If the panel board is main lugs only, the upstream overcurrent protective device must be sized to protect the panel board. Fourthly, branch circuit protection. Branch circuit breakers or fuses must be sized to protect the individual circuits that feed various loads. The size of the branch circuit protection depends on the ampacity of the branch circuit conductors and the type of load being served. Fifthly, motor circuit protection. Motor circuits require special consideration for overcurrent protection, as motors can draw high inrush currents during starting. The NEC specifies the maximum allowable overcurrent protection for motor circuits in Article 430. Sixthly, transformer protection. If the panel board is fed by a transformer, the transformer must be protected from overloads and short circuits. The NEC specifies the maximum allowable overcurrent protection for transformers in Article 450. Seventhly, coordination. Overcurrent protection devices within the panel board should be coordinated to ensure that the smallest overcurrent device closest to the fault opens first, minimizing the extent of the outage. Eighthly, selective coordination. In some applications, selective coordination may be required, meaning that only the overcurrent device closest to the fault should open while upstream devices remain closed. Selective coordination can improve system reliability and reduce downtime. Ninthly, feeder taps. If the panel board is fed by a tap from a larger feeder, the tap conductors must meet the requirements of NEC Section 240.21, which specifies the maximum allowable length and ampacity of tap conductors. Tenthly, conductor derating. Conductor ampacity must be derated for ambient temperature and the number of conductors in a raceway or cable, as specified in NEC Table 310.15b16 and NEC 310.15c. These NEC guidelines ensure that panel boards are properly protected from overloads and short circuits, minimizing the risk of electrical fires and equipment damage. Suppose you are sizing the conductors and overcurrent protection for a 100 amps panel board in a commercial building. The panel board will serve lighting, receptacles, and a small HVAC unit. Firstly, conductor ampacity. Calculate the total load on the panel board using NEC Article 220. Assume the calculated load is 80 amps. Referring to NEC Table 310.15b16, you find that a 3 American wire gauge copper conductor with a 75 degrees Celsius insulation rating has an ampacity of 100 amps, which is sufficient for the 80 amps load. Secondly, overcurrent protection. Since the panel board is rated for 100 amps, you would install a 100 amps main breaker to protect the panel board and the conductors feeding it. Thirdly, main breaker or main lugs only. In this case, you have chosen a panel board with a 100 amps main breaker. Fourthly, branch circuit protection. For the lighting and receptacle circuits, you would typically use 15 amps or 20 amps circuit breakers, depending on the load and the conductor size. For the HVAC unit, you would size the circuit breaker according to the motor's nameplate rating, following NEC Article 430. Fifthly, motor circuit protection. Size the motor circuit protection according to NEC Article 430, considering the motor's full load current, service factor, and temperature rise. Sixthly, transformer protection. In this scenario, there is no transformer directly feeding the panel board, so transformer protection is not required. Seventhly, coordination. Ensure that the branch circuit breakers are coordinated with the main breaker to minimize the extent of an outage in the event of a fault. Eighthly, selective coordination. Selective coordination may not be required for this application, but it should be considered if system reliability is critical. Ninthly, feeder taps. There are no feeder taps in this scenario, as the panel board is directly fed from the main service. Tenthly, conductor directing. Check the ambient temperature and the number of conductors in the raceway to determine if any directing factors apply. Adjust the conductor ampacity accordingly. By following these steps, you can properly size the conductors and overcurrent protection for the 100 amps panel board, ensuring compliance with the NEC and providing a safe and reliable electrical system. Regular maintenance of contactor-controlled panel boards is crucial for ensuring their reliable and safe operation. Firstly, visual inspection. Conduct regular visual inspections of the panel board, contactor, and associated wiring. Look for signs of damage, corrosion, or overheating. Secondly, cleaning. Keep the panel board and contactor clean and free of dust, dirt, and debris. Use a vacuum cleaner or a clean, dry cloth to remove any buildup. Thirdly, tightening connections. Periodically tighten all electrical connections in the panel board and contactor. Loose connections can cause overheating and arcing, which can lead to equipment failure or electrical fires. Fourthly, contactor inspection. Inspect the contactor's contacts for signs of wear, pitting, or corrosion. Replace the contactor if the contacts are damaged. Fifthly, control circuit testing. Test the control circuit to ensure that the control signal is properly energizing the contactor coil. Check the voltage and current of the control signal. Sixthly, insulation testing. Use a megameter to test the insulation resistance of the wiring in the panel board and contactor. Low insulation resistance can indicate insulation breakdown, which can lead to ground faults or short circuits. Seventhly, thermal scanning. Use a thermal imaging camera to scan the panel board, contactor, and wiring for hotspots. Hotspots can indicate loose connections, overloaded circuits, or failing components. Eighthly, lubrication. Lubricate the moving parts of the contactor, such as the armature and pivot points, with a suitable lubricant. Lubrication helps to ensure smooth and reliable operation. Ninthly, functional testing. Periodically test the operation of the contactor by manually opening and closing it. Check for any mechanical issues for binding. Tenthly, documentation review. Review the panel board's wiring diagrams and maintenance records to ensure that all maintenance tasks are performed according to schedule. These maintenance tasks help to identify and address potential issues before they lead to equipment failure or safety hazards, ensuring the continued reliable and safe operation of contactor-controlled panel boards. Consider a maintenance schedule for a contactor-controlled panel board in an industrial facility. Firstly, visual inspection. Conduct a visual inspection monthly, looking for any signs of damage, corrosion, or loose connections. Secondly, cleaning. Clean the panel board and contactor quarterly to remove dust and debris that can cause overheating. Thirdly, tightening connections. Tighten all electrical connections annually to prevent loose connections and potential arcing. Fourthly, contactor inspection. Inspect the contactor's contacts annually for wear and tear, and replace the contactor every 5 years or as needed based on the condition of the contact. Fifthly, control circuit testing. Test the control circuit every 6 months to ensure the control signal is properly energizing the contactor coil. Sixthly, insulation testing. Perform insulation testing annually to check for any signs of insulation breakdown that could lead to ground faults. Seventhly, thermal scanning. Conduct thermal scanning annually to identify any hotspots indicative of loose connections or overloaded circuits. Eighthly, lubrication. Lubricate the contactor's moving parts every 2 years to ensure smooth operation. Ninthly, functional testing. test the contactor's operation monthly to verify it opens and closes properly. 10th, documentation review. Review the maintenance records annually to ensure all tasks are up to date and to plan for upcoming maintenance needs. By adhering to this schedule, you can proactively maintain the contactor-controlled panel board, minimizing downtime and ensuring a safe working environment. Implementing safety measures when working with contactor-controlled panel boards is paramount to prevent electrical accidents and injuries. Firstly, de-energization. Always de-energize the panel board and contactor before performing any maintenance or troubleshooting tasks. Verify that the power is off using a voltage tester. Secondly, lockout-tagout. Implement lockout-tagout procedures to prevent accidental re-energization of the panel board while work is being performed. Place a lock and tag on the disconnect switch or circuit breaker. Thirdly, personal protective equipment. Wear appropriate personal protective equipment, including safety glasses, gloves, and arc-rated clothing when working on or near energized equipment. Fourthly, insulated tools. Use insulated tools that are rated for the voltage being worked on. Insulated tools help to prevent electrical shock. Fifthly, working space. Maintain adequate working space around a panel board to provide a safe area for performing maintenance and troubleshooting tasks. Sixthly, grounding. Ensure that the panel board and all associated equipment are properly grounded. Grounding provides a low impedance path for fault current, reducing the risk of electrical shock. Seventhly, arc flash hazard assessment. Conduct an arc flash hazard assessment to determine the potential arc flash hazard at the panel board. Use the results of the assessment to select appropriate personal protective equipment and establish safe work practices. Eighthly, training. Provide employees with adequate training on electrical safety, including the hazards of working with energized equipment, lockout-tagout procedures, and the proper use of personal protective equipment. Ninthly, confined space entry. If the panel board is located in a confined space, follow confined space entry procedures to ensure that the space is safe to enter. 10thly, emergency procedures. Establish emergency procedures for responding to electrical accidents, including procedures for providing first aid and contacting emergency services. These safety measures help to minimize the risk of electrical accidents and injuries when working with contactor-controlled panel board, creating a safer working environment for electrical workers. Let's say a technician needs to perform maintenance on a contactor-controlled panel board in a manufacturing plant. Firstly, de-energization. Before starting any work, the technician turns off the power to the panel board at the main disconnect switch and verifies that the power is off using a voltage tester. Secondly, lockout-tagout. The technician applies a lockout-tagout device to the disconnect switch to prevent anyone from accidentally re-energizing the panel board while they are working on it. Thirdly, personal protective equipment. The technician puts on safety glasses, insulated gloves, and arc-rated clothing to protect themselves from potential electrical hazards. Fourthly, insulated tools. The technician uses insulated screwdrivers, pliers, and other tools that are rated for the voltage of the panel board. Fifthly, working space. The technician ensures that there is adequate space around the panel board to work safely and comfortably. Sixthly, grounding. The technician verifies that the panel board and all connected equipment are properly grounded. Seventhly, arc flash hazard assessment. The technician reviews the arc flash hazard assessment for the panel board and confirms that they are wearing the appropriate level of personal protective equipment. Eighthly, training. The technician has received comprehensive training on electrical safety, lockout-tagout procedures, and the proper use of personal protective equipment. Ninthly, confined space entry. The panel board is not located in a confined space, so confined space entry procedures are not required. 10thly, emergency procedures. The technician is familiar with the plant's emergency procedures in case of an electrical accident, including the location of first aid kits and emergency contact numbers. By following these safety measures, the technician can safely perform maintenance on a contactor-controlled panel board, minimizing the risk of electrical accidents and injuries.